upload with the net zero, so that will last up to 4 minutes for the lift off, so that will be the beginning of which is today at 9, beginning of the window at 9:20 on the local time, 7:20 Eastern time. The final loading and end of the final loading.
And Luce, we're coming up on that final weather report. We expect all systems to remain green. We'll be going down to the fishbowl to confirm that just a moment or two from now. It's a 27-minute ride to orbit from liftoff until the time that the Webb Observatory is separated from the upper stage of the Ariane 5 rocket. Several minutes later, the commands will be given to unfurl the solar array, followed by the confirmation weather report. And Luce, we're coming up on all the systems to remain green, power positive, going down to the electrical current flowing just a moment through that solar array. With us inside the so-called fishbowl, seated with mission controllers on the floor of the control room from Raphael Chevrier of Ariane 5, separated from the Raphael has everything looking what's being discussed down there several minutes later to the Ariane 5 rocket to unfurl the solar array, followed by the confirmation to unfurl the solar array, followed by the confirmation of the telescope power positive, meaning Baltimore electrical current. We are power positive, that solar array. With us today inside the so-called fishbowl, seated with today inside the so-called fishbowl, room, seated with Raphael Chevrier on the floor of the control room. Raphael Chevrier of Ariane 5 there. Raphael has everything looking at what's being discussed down there.
At 7 minutes last operations that he described earlier before Webb change the Ariane 5 is going to lift off and so change to the sky was altitude winds, risk of landing.
Thanks, Raphael. We'll be back with you and Luce here shortly. So we now have confirmation from Baltimore that James Webb is on internal power. Amidst all of this activity, we cannot forget that it is Christmas Day. 53 years ago, the astronauts of Apollo 8 completed their 10th and final orbit of the moon after reading from the book of Genesis on Christmas Eve. Billions of people watching with rapt attention back on our planet. The astronauts then headed for home, following their spacecraft that we transferred from Baltimore shortly. Today, more than a half century later, amidst all of this activity, we cannot forget that it is Christmas Day. We cannot forget that it is Christmas Day. James Webb 53 years ago, the astronauts of Apollo 8. We're just 38 seconds away from entering the critical synchronized sequences. You're going to be hearing billions of all the critical calls from the DDO range operation manager headed for home, who is Jean-Louis Voyer, today more than a half century later. In the mission control center today, more than a half century later, we'll be calling Genesis synchronized sequence. All of the critical countdown milestones, and we will be listening very intently for just 38 stands away from entering. We're just 38 seconds away. You're going to be hearing synchronized sequence. You're going to be hearing the range operations calls from the range operations manager more than a half century later. With that, we've entered the period of synchronized sequence. Control started news fabric just a moment or two ago. Synchronized sequence explained some of the critical milestones. First one, we will be seconds away from entering topping off synchronized stage 2. The first or fourth stage was loaded earlier this morning with 175 tons of propellant, 150 tons of liquid hydrogen, and 25 tons of liquid hydrogen. The upper stage was loaded with 15 tons of propellant. That would be the workhorse of some of the work that will explain some of the critical finalities of the separation of the main 27 minutes and 7 seconds after launch. First, James Webb will be at an altitude of about 800 first or 175 tons earlier. To put that into perspective, some 520 miles higher, 25 tons telescope, and more than 125 tons International Space Station. The workhorse with 15 tons of propellant traveling about 21,000 miles an hour from the heads out to a highly elliptical halo-like orbit 7 seconds, 1 million miles from Earth. James Webb will be at an altitude of launch observation. James Webb will be at an altitude of to put that into perspective,
Now we will see some four times pressurized at the flight level for the last test and for the ignition of the Vulcan engine. And in parallel, the vector system are also setting flight configuration of the computer, the electrical power as for the telescope. It will switch from ground to internal power 1 minute before the launch, 1 minute and 5 seconds before the launch. And we are going to see now, we will see the 4 times at minus 6 seconds. We will see the disconnection of the last stage, this big cryogenic technique for the last test on this picture. And in parallel, the electric system. Then, 3 seconds before the parallel electric system, inertial part also set all the information about where it will switch, the launcher will be released, and it will switch before the launch to internal power before the launch. And we are going to see the main stage will start. We are going to see minus 6 seconds. We will see the disconnection a little less than minus 7 seconds, where the engine will start up to this flight regime. Once the computer has checked that the Vulcan engine is running normally, and you will see that both the flames will stable, inertial part of the launcher will be released, and at that point the launcher will be released, the 2 boosters that will enable to move the 7 stage posts of the main stage will start.
Coming up on the T-minus 4 minute mark right now, just a couple of milestones real quick. At the 1 minute 5 second mark into the flight, Ariane 5 will go through the period of maximum dynamic pressure, max Q as it's known. That will be the period of maximum aerodynamic forces on the rocket itself. The solid rocket boosters, which will provide about 90% of the initial thrust off the launch pad, will shut down and separate at the 2 minute 21 second mark into the flight, followed a minute and 5 seconds after that by fairing jettison. That will expose 1 minute 5 second mark into the flight, the environment of flight for the first time. The main stage separation of the first main separation comes at the T-minus at the 8 minute 47 second mark into the flight, rocket itself. The solid rocket boosters, which will provide about 90% of the initial thrust off the launch pad at about 24 minutes, 51 seconds into the flight, and then we'll go into our post-phase of about 2.5 minutes to allow any oscillations to dampen out, to provide the most pristine environment for the first time to the main stage separation before observatory separation comes the main stage separation of the first stage separation. Coming up on the 2-minute-50 second mark into the flight, again, you're going to be hearing critical calls down stage here from the DDO, or the Range Operations Manager, Jean-Luc Voyer, at about 24 minutes, 51 phase of about 2.5 minutes, and then we'll the weather is go. We have a green board, no issues being working oscillations to dampen out. NASA officials, including Steve Robinson on the right, carefully watching the telemetry separation, coming up on the looking intently at the final couple of minutes of the countdown. Live, you're going to be hearing second calls preparation here again. The James Webb Space Telescope down the stretch here from Jean-Luc Voyer, the Range Operations Manager, Jean-Luc Voyer.
From Iron Space.
The weather is go. We have a green board. No issues. The weather is go. We have and that is the DDO, the Range Operations Manager, Jean-Luc Voyer, carefully at the 2-minute mark in the country. On the right, carefully looking intently at the telemetry. Couple of minutes of the countdown lives have been spent. At the final couple of minutes of the countdown lives of the James Webb Space Telescope. The preparation of the James Webb Space Telescope
will be in 2 phases. You will see the first part of the flight during the solid rocket boosters phase. That will be the atmospheric part of the flight.
And that is the DDO, the Range Operations Manager. That is the DDO, the Range Operations Manager, Jean-Luc Voyer, as we have hit the 2-minute mark in the countdown.
Exo-atmospheric flight after that.
And you were watching a number of people, VIPs and invited guests, moving out to the observation platform that is right next to the Jupiter Control Center as we stand by for the 1-minute call from Jean-Luc Voyer.
Attention pour moi, j'ai une minute.
And the trajectory will be driven by a very, and we will have a very different flight. We will have a very different
thumbs up from Jean-Luc Voyer. All systems are go. We're inside a minute now. And you were watching a number of people, VIPs, as you heard earlier, the Vulcan 2 engine will ignite. That is right next to the turbo pumps will come up at flight speed for 7 seconds, and the command will be issued to ignite the solid rocket booster. The James Webb Space Telescope will be on its way.
We're not going to be quiet, but we're going to mute our mics so you can't hear us.
Top, à 0 moins 1 minute.
T-minus 30 seconds from Jean-Luc Voyer. All systems are go. We're inside a minute from Jean-Luc Voyer. All systems are go. We're inside a minute now. T-minus 50 seconds and count. The Vulcan 2 engine standing by for terminal count. Turbo pumps the Vulcan 2 engine will ignite for 7 seconds, and the command will be issued to ignite the solid rocket boosters, and the command will be issued to ignite the solid rocket boosters. The James Webb Space Telescope will be on its way.
5, 4, 3,
T-minus 30 seconds and counting.
unité, top.
T-minus 30 seconds and counting. And we have engine start. Standing by for terminal and liftoff.
Décollage.
Standing by for decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
6, 6, 5,
Punching a hole through the clouds, 20 seconds into the flight. Good pitch program reported.
unité, top.
And we have engine start.
Trajectoire
And we have
irrégulière.
engine start and
Allumage
liftoff.
EAP, décollage.
Vehicle performance is not liftoff from a tropical rainforest to the edge of time itself. From a tropical rainforest to the edge of time itself. Ariane 5 rocket continues a voyage back to fly uphill in nominal fashion. Punching a hole through the clouds. 20 seconds into the punching a hole through the program. Rumble of the powerful Ariane 5 program here in the control center. 3D animation.
Trajectoire
Vehicle
illuminale.
performance is nominal. Vehicle performance is nominal. 13 kilometers in altitude, 7 kilometers downrange. Rocket continues traveling to fly about 0.6 kilometers per second. Uphill in nominal
Tous les
fashion.
paramètres à bord sont normaux.
The rumble of the powerful Ariane 5 trajectory reported to be nominal by Jean-Luc Voyer, the range operations 3D animation. You can see at the bottom of your screen, the yellow line is the trajectory plot, perfectly overlaid over the green line, 13 kilometers in altitude, 7 kilometers down, 13 kilometers in altitude, 7 kilometers down, about 40 seconds away from shutdown of the solid rocket boosters, 0.6 kilometers per second.
Tous les paramètres à
The
bord sont normaux.
trajectory reported to be nominal by Jean-Luc Voyer. Coming up on the 2-minute mark into the flight by Jean-Luc Voyer, the range operations manager. The yellow line is the trajectory plot of your screen. The yellow line is the green line, which is perfectly overlaid over the green line, which is 1 minute 41 seconds into the flight. About 40 seconds away from seconds into the flight of the solid rocket boosters. 2 minutes 15 seconds into the flight of the solid rocket boosters.
When the computer detects this threshold, it will separate.
Coming up on the 2-minute mark into the flight.
Séparation des EAP.
Coming up on the 2-minute confirmation of solid rocket booster separation from Jean-Luc Voyer. This coming at an altitude of 44 miles. The Ariane 5 and James Webb traveling almost 5,000
Tous les
miles an
paramètres à
hour.
bord sont normaux.
Less acceleration.
We have
Tous les
about
paramètres à
1
bord sont
minute
normaux.
5 seconds to go before
2 minutes,
15
15
seconds into the flight. The next critical milestone. 2 minutes 15 seconds into the flight.
Threshold. The fairing is there to avoid the satellite being exposed
Séparation
to
des
high
EAP.
temperatures
We have
and also
confirmation
high
of solid
Séparation
rocket
des
booster
EAP.
separation
As soon
from
as
Jean-Luc
launch
Voyer.
confirmation
Of solid
leaves
rocket
the
coming at an
atmosphere,
altitude of
as is now
44
the
miles.
case, the satellite does
The
not
Ariane
need a
5
door
and
for
James
protecting
Webb
them.
almost 5,000
Webb
miles.
does not need
Ariane
a
5
more
and
to
James
Paramètres à
Webb
bord sont
traveling
normaux.
almost 5,000
So
miles
keep
on
your
1 minute 5
being very
seconds to go
important for
before
the performance of the
about
launch.
1 minute
We
5
are going to
seconds to go
inject
before
this no
fairing
more
jettison.
useful
That'll be the
fairing.
next critical milestone.
The fairing is there to avoid the satellite
And let's go
being
down to the
exposed
floor
the fairing
in the
is there
Jupiter
to
Control
avoid the
Center
satellite
to
being
Raphael
exposed
Chevrier
to
of
high
Ariane
temperatures.
Space. Raphael, so far so good.
Leaves the
Hi, Rob. So
atmosphere as
far,
soon
so
as
good.
the
Everything
launch.
is
The
nominal
satellite does not
as
need a
we say with
multiplier
altitude and
case.
trajectory
The
of
satellite
the
does
Ariane
not
5
need
is
a
going to
multiplier
Paramètres à bord sont normaux.
well, as you can
So
see
weight
also
does
on
not
the
need
so
more
on
to
the
be
Paramètres à bord sont
very
normaux.
important for the performance of the launch.
we had
We are
confirmation
very
of
important
the
for this performance
separation
more
of the
useful.
two
We are
systems
going to
and now
inject
of
this
the
no more
fairing, meaning
useful
that we have
fairing.
crossed
And let's go
the
down to the
limits
floor
of the
in the
atmosphere.
Jupiter Control
So
Center.
everything
And
is
let's
going
go down
well.
to the floor in the
And
Jupiter
the
Control
control
Center. So far so
center
good. Raphael Chevrier of Ariane Space. Raphael, so far so good.
So let's continue the mission.
And Raphael, this is a view from the upper stage camera called the Vicky Cam, looking back at the James Webb Space Telescope. This is on about a 20-second delay or so because of the way the imagery is processed here in the control room. There's your telescope ready to unfurl its wings basically and begin its journey to the Lagrange point, the L2 point, about 1 million miles away from Earth. This is a view from the upper stage camera. This is a view from the upper stage camera. Trajectory is nominal. The report from Jean-Luc Voyer, because telescope, the way the imagery is processed delay or so here in the control room, the imagery is processed here in the control room. The liftoff time confirmed here in the Mission Control Center at 12:20 Greenwich Mean Time, 9:20 a.m. Peru time, 7:20 a.m. Eastern Time, about 1 million miles away from Earth. The Ariane 5 and James Webb, 181 kilometers, the report from Jean-Luc Voyer, 400 is nominal, the report 50 kilometers downrange from the launch site here in Peru. The liftoff time confirmed here in the Mission Control Center at 12:20 Greenwich Mean Time, in the Mission Control Center at 12:20 Greenwich Mean Time, 7:20. We have about 3.5 minutes to go in main stage or first stage performance. And again, you can see at the bottom of your screen the yellow plot line overlaid over the green line, meaning we are right on course, right down the pipe in a perfect trajectory so far for the Ariane 5 rocket.
Flight control is very
5 minutes, 12 seconds into the flight.
Telemetry data are
We have about 3.5 minutes to go
tracking station,
in main
stage,
stage or first stage of
where we are
performance. In main stage or first stage of your screen, the yellow, and again, you can see at the bottom of your screen, the yellow meaning we are right on the green line, down the pike, and perfect trajectory so far for the Ariane 5 rocket trajectory so far for the Ariane 5 rocket.
in the middle of the ocean, and the two last stations in Africa, Libreville and Malindi, one on the east coast, the other one on the west coast, where we are, and the one on the west coast, which is close to here, where we are. Satellite between the telescope will be separated more or less over this Malindi station. This Malindi station will also require the telemetry station in Brazil. We can see both data station, Brazil, and the mission, and they are exploring the stations receive the data. It was confirmed right now by the East Coast, the other one on the West Coast, operations manager, one on the East Coast, the other one on the West Coast, and the one on the West Coast will be
Just confirming now that telemetry is being processed through the Brazilian tracking station. The telescope is also processing telemetry through the tracking and data relay satellite system. As it moves further and further out into deep space, all of the telescope's telemetry and its imagery ultimately will be processed through the Deep Space Network in Goldstone, California. Past the 7-minute mark into the flight. A perfect ride so far on the Ariane 5 being processed through the Brazilian tracking station. Being processed through the Brazilian tracking station telemetry. The telescope once the main stage engine commanded to cut off further satellite will be jettisoned. All of the moves further and further out of that. The upper stage engine will ignite process telemetry and will be the workhorse for Goldstone. 16-minute burn. Deep space 7-minute Webb in the flight preliminary. Perfect ride 7-minute so far on the Ariane 5. Perfect ride. We have about 1.5 minutes to go. We have about first stage performance. 1.5 minutes to go. Once the main stage engine is commanded to about 11 minutes from now, telescope controllers, just a few seconds telescope science engine will be sent a few commands after that. James Webb for the initial series burn commissioning activities James Webb that will lead to the deployment of its James Webb into its preliminary initiation of generation of electrical power for the telescope. About 30 seconds away from main engine cutoff. About 11 minutes from now, telescope controllers at the Space Telescope Science Institute will be sent to the Space Telescope Science Institute. Nominal trajectory continues mission watchwords for the range operations activities. Solar array to the deployment of the standby main engine shutdown and separation of generation of electrical power for the 30 seconds away from main engine cutoff. About 30 seconds away from main engine cutoff.
Extinction de l'EPC. La trajectoire est normale.
Nominal trajectory continues to be the watchword. Nominal trajectory continues main stage shutdown and separation confirmed here in the Mission Control Center. And the ignition of main engine shutdown and separation. And Raphael Chevrier down in the fishbowl. So far, so good.
Yes, Rob, we have the confirmation of the separation of the main stage and the ignition of the upper stage. The trajectory is perfectly nominal. This is a very important moment for us because it's always a challenge to switch on a cryogenic engine in space condition, and we are now
confirmed here in the mission control center, shutdown and the ignition of that first in the mission control center, and the ignition of that fishbowl, Raphael Chevrier down in the fishbowl.
We have the second phase of the main stage. Yes, we have the confirmation of the power and the ignition in about 16 minutes to place Webb on its transport orbit, and right now everything is again nominal for the DBO engine in space condition, and we are now cryogenic engines.
And a short time from now, the so-called sawtooth maneuver will get underway. That's again like rocking a baby in a cradle. This will be a maneuver to keep Webb's optics protected from overheating.
The second power for the flight.
You can see here Webb attached on top of Ariane 5 upper stage with a very specific configuration. Of course, it will be different during its lifetime, but for the time being,
and a short time from now, the so-called and a short time from now, we get underway the sawtooth maneuver, rocking a baby in a cradle. This will be a maneuver to keep Webb's optics cradle. This will be a maneuver to keep Webb's optics protected from overheating.
on the time you can thermal conditioning inside the telescope, and the way the rays with a very specific configuration of interact with a very specific configuration inside the telescope. During its lifetime, for the time being, it's really key not for full separation this telescope. And we know that one phase of the telescope cannot phase with the sun. That's why the produce these right thermal conditions inside the specific roll low, the way the rays inside what we call the sawtooth approach, the rays if you are working carefully to this telescope with animation inside the telescope. The upper stage is going 30 degrees on one side, then 30 degrees on the other side, going back and forth this way to maintain this perfect thermal conditioning for the telescope.
It's worthwhile noting that after Webb separates from the upper stage of the Ariane 5 rocket, which continues to perform in excellent fashion, and is coming up on the 12-minute mark into the flight, the telescope controllers will be taking the baton, if you will, from the mission controllers here in Peru. The first steps will be the opening of fuel valves, a pair of fuel valves, to start flowing fuel to Webb's onboard thrusters. Worthwhile noting that after those are powered on the operation control and fire those thrusters of the Ariane 5 rocket, which Webb coming up on the 12-minute mark into the flight at approximately on the 12-minute mark into the flight will be taking the baton, if you will, locked in place, will be taking the baton, if you will, electricity is flowing through the array. Fuel valves, that first step from the mission operations fuel valve, pair of thrusters, who is at the Space Telescope Science Institute of Johns Hopkins, those are powered on through the operation electronics in that control room powered on in operation to control and fire those thrusters when they're deployed at James Webb. The discovery of 3 minutes mark is approximately the lead 33 engineer for launch and ascent. Electricity is flowing through the array. That electricity is from mission operations manager Carl. 3 out of the 4 mission operations for the after-deployment radiator to be released at the Space Telescope Science Institute of Johns Hopkins in that control room is decontamination control heaters will be enabled to protect the instrument optics on Webb from any water ice condensation as they cool down. The actuator drive units will be powered on. This particular mechanism helps with ascent control. Condensation later to be used to position each of the deployed segments will be released. All 6 reaction wheels and the wheel drive electronic control heaters will be enabled. And that type of control heaters will be enabled control system using those reaction wheels to maintain proper drive units will be powered on as opposed to using
This Sunshield is no ordinary umbrella. It's going to be irradiated by 200,000 watts of solar radiation. And it should only allow about 0.02 watts through. So if it were suntan lotion, it would have an SPF of about 10 million. And the way we do this is the Sunshield is composed of 5 individual layers, each about the size of a tennis ball. The first layer facing the sun will reflect most of that 200,000 watts that hit it. But of the small amount that gets through, that wattage, that power, will reflect back and forth between the first layer and the second layer until it eventually bounces out the edges. And that small amount of power that gets through the second layer will then bounce between the second and third layer and eventually go out the side. So here we have this, the James Webb Space Telescope. When it's integrated with the telescope and the Sunshield, we'll have an observatory that stands about 3 stories tall, is 6 metric tons. It's about the size of a tennis court, and the telescope will be below 55 degrees Kelvin. This is a very challenging mission. Now, you can see the telescope and the observatory have 4 major parts. First, the telescope itself, that we call the OTE, optical telescope element. And it has that large primary mirror consisting of 18 individually controlled segments. Behind it are the 4 science instruments that are integrated into a common assembly that we call the ISIN, the Integrated Science Instrument Module. Then we have that big umbrella, the Sunshield, consisting of 5 layers. And on the hot side of the Sunshield, we have the spacecraft bus. And that spacecraft bus has the traditional spacecraft subsystems: electrical power, telecommunications, guidance and navigation, that kind of thing. So with an area of about the size of a tennis court, James Webb does not fit into the launch vehicles we currently have. And to fit into the Ariane 5 launcher, which has a 5-meter diameter fairing, we have to fold the telescope up. Let's fold the observatory up. And that means we have to unfold it on orbit. A very complex and challenging procedure. Now, when I started in this business about 40 years ago, I remember one of the first lessons I got taught was avoid deployments on orbit. James Webb cannot avoid the deployments. In fact, James Webb has to perform some of the most complex sequence of deployments ever attempted. And these come with many challenges, but I categorize the challenges into 2 broad categories. The first challenge is that many of these deployments are what I'd call precision deployments, particularly those of the telescope. Now, think of what we're doing here. We've built a world-class infrared telescope. We've built it, we've aligned it, we've tested it, we've proved it works. Now we're going to have to break it up, fold it up, and actually rebuild it on orbit, rebuild it, realign it, retune it, and get it to work robotically on orbit. That's never been done before. And this rebuilding, this alignment, are to optical tolerances. And to put that in perspective, what that means is any light ray through the telescope has to have an error no greater than 150 nanometers from its prescribed path. And if you want to know what 150 nanometers looks like, well, that's about 1/670th of the width of a piece of loose leaf paper. Now, the second set of challenges comes because a lot of these deployments involve floppy, indeterministic members like those big Sunshield layers that we talked about. You know, NASA is used to deploying rigid beams on hinges because they're deterministic. You can control how they move. But these, when I say something is indeterministic, I want you to, that's illustrated by this example. Take a string and put it on a tabletop and push it. And see if you can predict the shape of that string. Chances are you will not be able to. And so it is with the membranes of the Sunshield. So we can't really predict their shape, but we can constrain it. We can try to prevent it from going in places that we don't want it to go, places where it could snag or tear or maybe impede the deployment of other members. We do that by building in restraint mechanisms. And there's going to be a lot of these restraint mechanisms when you're talking something the size of a tennis court. We've done extensive studies, we've done extensive experiments to determine just how many of these release devices we want. You see, we want to have enough devices to control the Sunshield, but not too many to add unnecessary failure modes. Now, we've done these exhaustive studies, and the answer we came up with was reviewed by various independent review groups. In the end, we've all agreed. We found the sweet spot on it. We found the right mix of mechanisms. The final part of the mission that I want to talk about that's a little unique is our orbit. We're not going to be orbiting the Earth. James Webb will operate around the Sun-Earth second Lagrangian point. Now, that's a point 1 million miles away from the Earth, 4 times farther than the Moon, on the opposite side of the Sun. It follows the Earth around the Sun every 365 days. And it's a point where the gravity of the Earth and the gravity of the Sun combine to make a relatively stable point. Now, our Ariane 5 launcher will put us on a direct inject path out there, and it'll take about 40 or 50 days to get out at that distance. And during that time, we'll do 3 mid-course corrections. We'll do our deployments that you'll hear more about in a second. And around 40 or 50 days after our launch, we will actually fall into a little orbit around the L2 point. By that time, we will have cooled down and we will be calibrating our instruments. And at launch plus 180 days, the observatory will be commissioned and we'll be ready for our science mission. And during that science mission, we will execute an orbit around the L2 point that takes about 180 days. Now, because the L2 point is only close to stable, we have to do station keeping maneuvers to stay in that orbit, and we'll do station keeping about once every 21 days. And now to talk more about the deployments, our deployment systems lead, Alfonso Stewart, will come up and give a better explanation of some of these.
Thanks, Mike. Here at the launch facility in French Guiana, helping to prepare Webb for the integration to the launch vehicle. You've heard about the science goal from Begonia and the overall design of Webb from Mike, but what I'm going to talk about is the nominal deployment sequence we're going to go through in order to achieve the deployed state. So what is origami? Like an origami object, proper folding and unfolding is necessary in order to achieve a specific shape. And Webb will do origami in reverse, meaning that it will unfold in a certain sequence. Now, you may have also heard the reference 29 days on the edge. And what that means, there are 2 important times in that deployment scenario. There's the launch, and also at L plus 28 days, there's the thruster burn to insert Webb into its operational orbit. The timeline we're going to talk about today is the nominal timeline. However, we do have the flexibility within that timeline to adjust if necessary. Now, at the start of deployment, the predicted temperature is approximately 20 degrees C, about room temperature. However, over the deployment timeline, the temperature will decrease down to negative 200 degrees Celsius. The first deployment is the first set of deployments are the solar array and high gain antenna. So why the solar array first? Well, electrical power is required for the observatory to function, and the battery can only last a few hours, so we need the solar array to be deployed in order to continue with the mission, and then followed by the high gain antenna for the necessary communication capabilities in order for us to continue the commissioning activities. In preparation for the Sunshield deployment, the UPS, or unitized pilot structure, deployment tower assembly, and the trim flaps are deployed. Then we start the Sunshield deployment sequence. That sequence starts with the membrane cover release as shown here in the graphic, followed by the mid-boom deployment that pulls out the membrane and radiator shade. Next, we have the OTE assembly that deploys the secondary and primary mirror assembly. Now, in addition, as I mentioned before, this is a nominal deployment sequence that we're planning. However, Webb uses contingency operation in the event of an anomaly deployment action. Now, these operations range anywhere from the simplest, such as checking the telemetry and resetting the command, to a more complex operations such as switching to a redundant system, or we can also use what we call excitation of the observatory, what we aptly name shimmy, twirl, and fire and ice. And now we have Crystal Puga that will describe the most complex of these deployment in further details. Over to you, Crystal.
Thanks, Alfonso. I'm here in the launch site control room in the satellite processing building in French Guiana. This is the room where Webb engineers will monitor the observatory's state of health on the day of launch using the telemetry you see on the screens behind me. So as the other speakers mentioned, the Sunshield is a critical part of the observatory. It has one simple task. It needs to protect the observatory by blocking the heat from the sun, the earth, and the moon. Although it's a task, it is worth diving deeper to truly understand the truly pioneering system and how the sophisticated umbrella works. The Sunshield separates the web into the hot and the cold side. On the hot side of Webb, it is a toasty 260 degrees Fahrenheit. Meanwhile, on the cold side, it's a freezing negative 300 degrees Fahrenheit, which is colder than any place on Earth. That's a roughly 600-degree temperature differential, which is accomplished passively using 5 tennis court-sized Sunshield layers made out of a special material called Kapton. Kapton has unique thermal properties that are needed to keep Webb cold. It's highly resistant to heat and remains stable across a large temperature range without burning or melting. On Earth, Kapton is typically used as an electronic insulator and is actually a translucent amber color. So, in order for us to accomplish the heat radiation bouncing technique that Mike described in an earlier section, we first need to enhance the Kapton even more. First, we coat it with an aluminum on both sides, which makes the membranes reflective, allowing for that bouncing and for the heat to be able to reflect out in between the layers. We also apply a silicone treatment, which is applied on the sun-facing side of the 2 hottest layers, which is the silicone is actually even more effective at radiating the heat back into space. This also gives the Sunshield a soft purple color that you see on the bottom of several of the images. The Sunshield Kapton material is super lightweight, and in fact, it's really thin. It's only about the thickness of a human hair. And I have a sample here with me. You can see the sample. It's very crinkly, and it's very, very thin. In order for us to construct the Sunshield, we actually put it together like a quilt using patches of this Kapton that we thermally bond together. So you can see a bond here, thermal bonds, putting 2 of these pieces together. Those bonds create about 10,000 seams. Each layer has a unique template because each layer is actually slightly different in size and in shape. To strengthen the membranes, we actually add reinforcement strips about every 6 feet. These reinforcement strips act as ripstops to help eliminate or contain any tears or holes that are caused by micrometeoroids. The metallic ribbons also help provide structure to the membranes. Before we get into the Sunshield deployment, we first need to address the stowing process, which is just as critical. The Sunshield has to be packed away to fit inside of a 5.4 diameter rocket fairing. The folding process has a very specific sequence. First, we carefully fold back and forth accordion style using engineers that are fully trained and know not to handle the material very delicately to avoid any creases or tears. They also use a specially designed folding fixture to allow them to do that. After we fold each Sunshield membrane, we then fold it up in between around all of the sensitive telescope and optics. So we need to make sure that when we deploy, we don't accidentally snag on any of those sensitive components. Um, our Sunshield is very similar. It's our lifeline, similar to like a skydiver's parachute. It needs to be folded perfectly so that it unfolds and deploys perfectly without those snags, without any tangles. Now to the Sunshield deployment. I think of the Sunshield deployment similar to like a Rube Goldberg machine in that it uses a series of reactions that work in successions, triggering one event after the other until the entire Sunshield is fully deployed. Some of the key hardware include 140 release mechanisms, about 70 hinge assemblies, 8 deployment motors. We have several bearings, springs, gears. About 400 pulleys are needed, and 90 cables totaling 1,312 feet. The Sunshield deployment starts on day 3, just after we pass the moon, and it will take approximately 3 days to fully complete. First, we're going to release the large pallet structure that holds the membranes. We'll do the forward side and then the aft. Next, we're going to release the special restraints that hold the protective covers and roll them out of the way. Next, we're going to release a set of curves that are on the core region. At this point, we're ready to actuate the 140 release mechanisms, which all must work perfectly. They're all single-point failures. They all need to work perfectly in order to release the Sunshield. 2 large motor-driven telescope structures called mid-booms will extend the Sunshield in the horizontal direction, revealing the iconic diamond shape. The very last step is super important. We need to tension all of the membranes using a series of pulleys and cables to create that separation between each of the 5 layers. To perfect this Sunshield deployment sequence, we performed multiple deployment testing over several years on both small and full-size models. We practiced not only the deployment, but also the stowing process. We have a rare program. This gives us the confidence that Webb is going to deploy successfully in orbit later this year. So with that, I will turn it back over to Laura for Q&A.
Thanks, Crystal. Now we're opening our line for questions. If you're watching this on your device at home, would like to ask a question, be sure to mute your device before asking your question. Operator?
At this time, if you'd like to ask a question, please press *1 and clearly record your first and last name. Again, that is *1 if you have a question at this time. Our first question comes from Bill Hardwood. Small and full-size model.
Yeah, thank you very much. Making sure you can hear me okay?
Yep, we can hear you, Bill.
Okay, yeah, thanks. I'm curious as to what the limits are, temperature-wise, to still have a successful mission. And what I mean by that is, if the sunshade, if all the layers don't fully deploy and separate exactly as planned.
Down in the fishbowl where there is jubilation, let's go to Raphael Chevrier of Ariane Spas. Let's go to Raphael Chevrier of Ariane Spas. And before we do that, Raphael, the solar array happened a bit earlier than planned, but there is the solar array having been to ray out.
We do have
some confirmation that and there it is. There's your critical call. James Webb not only has legs, but it has power as it begins its journey and the commissioning activities to follow. And with that, let's go down to the floor in the fishbowl and Raphael Chevrier of Ariane Spas.
This is it. We have witnessed the confirmation that Ariane 5 has safely delivered Webb into space. The upper stage is now being placed on the stage.
There it is. There's your critical call. James Webb, and there it is. There's your critical call. James Webb not only has legs, but it has power activities to follow. And with that, let's go down the activities to follow.
If it was more global then we started to eat significantly into that 80% margin, then we'd start to have a problem. But for our near instruments, that would be the degradation would be graceful. And I don't have an exact number for you in terms of temperature on that, but I would suspect that detector temperatures probably of around anywhere between 45 and 50 degrees Kelvin could still be tolerable to our in the near.
Here in the Space Telescope Science Institute, their work just beginning on a new era of scientific
Our next question comes from Marcia Dunn. Your line is now open.
Yes, hi. I have some questions for Mr. Metzel again. Certainly, the Sunshield deploy, correct me if I'm wrong, but it certainly sounds like the tensest, most hairy, the most hairy part of the whole deployment. Is that true in your mind? Is this really going to be the most dramatic part of the whole early part of the mission? And how much of a gap is there between the layers? I'm wondering, the size of a tennis court, but how thick, if I were looking from the side once deployed, how thick would this be? And lastly, if I'm looking at this tennis court size Sunshield, do you have to have at least, would you guess, half of it deployed properly in terms of, how the perimeter? I mean, just 3/4, or is it, or can you not really specify? Thanks.
Okay, well, first to your first element, yeah, of all the things that that I'm, I guess I don't want to say worried about. The things that we focused on for deployments is definitely the Sunshield for reasons, at least personal reasons that I've already elaborated on. The Sunshield is one of these things that is almost inherently undeterministic, unlike the things on the OTE, where once again we have rigid booms that are on hinges and latches that we know how to control. Although we've certainly focused on that. So the Sunshield is the one that has some risk to it. We've certainly tried to concentrate on it. In terms of your other question as to the different failure scenarios, it would be, I don't think that I would say that if half of it didn't deploy, we wouldn't have a problem. We certainly would. As to, if portions of it didn't deploy exactly the way we wanted to, a lot of that would depend on where the misalignment was. But as I said, we have cryogenic margins for some of that. And if the imperfection was localized, let's say to something around 12% of the perimeter didn't have the gap we want, we would probably be okay with that. As for the exact gap as for the exact dimensions between the gap, I think I might see if Crystal might want to answer that. I think it's of the order. The largest gap we have might be of the order of about 0.8 meters, or somewhere between 1.5 meters and a meter. If Crystal would want to correct me on that.
Yeah, so we do have a separation about 16 to 18 inches in between the layers. It actually the distance varies because if you look at the photo of the James Webb, it's actually closer in the core region. There's actually a smaller gap, and as you extend out towards the edges of the Sunshield, the gap gets a little bit bigger, and this helps again with kind of that bouncing of the heat in between to radiate it out, which is why it's a little bit wider on the edges.
To get some reaction from him. In South European spaceport, the mission controllers there are the team, a fantastic job. Controllers utterly flawless.
In the meantime, while we're waiting on the
our
next...
Our next question comes from Chelsea Goes. Your line is now open.
Thank you. Chelsea Goes with Space.com. As you've all illustrated, Webb clearly has a very complex deployment ahead of it. Could you talk a little bit about the kind of contingency plans you have in place? As I assume any anomaly at any of these stages of deployment would require perhaps multiple contingency plans, and how much pressure is on the team to get this right?
That's another good question for Mike.
Well, we do have multiple contingency plans, and I'll turn it over to Alfonso to talk about some of them in detail. Some of these plans have been pre-formulated for the more, time-critical deployments, and there's only one deployment really that's time-critical, and that's to get the solar array out. So we have some pre-formulated, pre-canned deployment plans, or contingency plans for that. For the other type of deployments, I'll talk to Alfonso a little, or I'll hand it over to Alfonso to talk a little more about that.
Yeah, thanks, Mike. Yes, there are numerous deployment operation or contingency operation that we have. And as I mentioned before, the contingency range anywhere from the simplest to the more complex. And I mentioned as an example, you can simply send the command again. Also, there are quite a bit of redundancy in the system. We have multiple ways of sending the same signal. In some cases, it's just a telemetry. In order to know that you have an anomaly, it could be just you have an erroneous telemetry. So we have redundancy telemetry, or we can check and verify a telemetry through other means. So there's quite a bit of redundancy. In addition to over the past years or so, the team have been practicing these contingency scenarios where an anomaly is introduced and the team will work to try to solve it in a sort of rehearsal plan. So both the design from in terms of redundancy and features in the mechanism, as well as procedures and the way we operate and the way we deal with these, we have been practicing and using and exercising those systems over the year to anticipate and to deal with these anomalies if they come up. So yes, we have been practicing quite a bit for that.
Everybody here at the Baltimore Space Center incredibly Charlotte Best first actions.
Our next question comes from Stephen Clark. Your line is now open.
Most of her professional life in human spaceflight.
Thank you for taking the question. I think my question is probably for Mike or Alfonso. Are there any areas in any of the deployments where there could be a single point failure? If there's an area where something doesn't work, it would be very difficult to recover from that, like a mechanical structure or an electrical system or anything like that. And also, the deployments of the mirrors and the Sunshield, do those, and I know you said you have some flexibility in the schedule, but do they have to happen before you get to L2, or could you, push that weeks, beyond the scheduled intended date if necessary? Thanks.
Let's start with Alfonso.
Yes. Let me take the last one first. The question, I believe the question was about do we have flexibility in the schedule for the mirror deployments? Yes, we do. The nominal deployment sequence is that we start the mirror deployment over approximately a 9-day period at around L plus 14 days. However, that deployment can occur much later into the program, even after the second burn at L29. So we do have quite a bit of flexibility in the mirrors. Now, I think the first question you asked about other flexibilities we have or single point failures. Yes, we have identified single point failures in the system, and once we've done that, we have very detailed and extensive testing, and review of the design, and just to make sure that these things are the reliability or such. But there are single point failures on the system. I don't remember the quite number. I think Mike, if you remember the numbers, but there are quite a bit of single point failures. I mean, single point failure system on the observatory. But we have identified those, and we have developed really rigorous test plan and operation procedure to deal with those. Yes.